Periodic trends, atomic radius, and ionization energy. There are four main trends in the periodic table: the atomic radius, electronegativity, ionization energy, metallic character. These trends are all shaped by the interactions between the positive charge of the atomic nucleus, the negative charge of the inner electrons, and the negative charge of the outer electrons, or valence electrons. Due to the increasing size of atomic orbitals at higher energy levels, we expect the atomic size to increase as the period increases. So as you go down this way. Due to the effective nuclear charge when moving from left to right across a period, we would expect atomic size to decrease when moving across a period. The next slide shows the actual data. Atomic radii trend. What is the trend in atomic size across a period? What's the trend in atomic size down a group? Well, you probably don't know yet, so we're just going to pull this aside and look at it and see what we can come up with. As you go across the periods, right, that's in that direction, we can see that the size of the atom gets smaller. And as we go down a group, we can see that the size of the atoms get larger. We're going to spend some time now explaining why that happens. Now let's get into ionization energy. A neutral atom has equal number of protons and electrons. For example, a neutral magnesium atom has 12 protons, each with a positive charge, and 12 electrons, each with a negative charge. So it has a net zero charge. Your 12 plus your 12 minus, and you get a net charge of 0. The ionization energy is the amount of energy required to remove an electron from an atom. When you remove an electron from an atom, you wind up with a positively charged ion, which is known as a cation. And a nice way to remember that is a cation is positively charged. Cats have paws, or you can just remember it. So we have magnesium here. We take the electron away, and we're left with magnesium plus. So it has 12 protons, 11 electrons, 12 minus 1, positive 1. Net charge is positive. And here's the electron that left. The first ionization energy is the energy required to remove the first electron, which we showed on the previous slide. The second ionization energy is the energy required to remove the second electron. So now we've got 2 electrons taken out. So we have magnesium goes into magnesium 2 plus 2 electrons. And that's the second ionization energy. Applying Coulomb's law helps us understand how ionization energy changes among elements. So we'll start with lithium. It has these 2 inner electrons shielding 1 valence electron. Beryllium, 2 inner electrons shielding 2 valence electrons. So what is the force between the nucleus, the protons in the nucleus, and the valence electrons? Well, for lithium, this guy is shielded by these 2 electrons, so it has an effective nuclear charge of just +1. So the force is Ke squared over R squared. For beryllium, again, you have the 2 shielding electrons here, but you have 4 protons. So you have a charge of 2, right? You have 2 basically 2 positive charges acting on your beryllium valence electrons. So the force on each of beryllium's electrons is 2 Ke squared over R squared. Which atom is held together more closely? Since beryllium holds on to its electrons tighter, it holds them more closely. So it will require more energy to take away an electron. The ionization energy of beryllium is higher than lithium. As electrical force increases, the atom holds on to its electrons tighter. The nucleus is attracting them stronger. It will require more energy, and that's ionization energy, to take them away. As force increases, ionization energy increases. So how does Coulomb's law affect the atomic radius? How will it affect the ionization energy? And how will the trend in atomic size relate to the trend in ionization energy? It's always good when you can tie together different phenomena. As the electrical attraction between the nucleus and the outer electrons increases, which is shown by Coulomb's law, the atomic radius decreases and the ionization energy increases. The trend of atomic radius and of ionization energy have an inverse relationship. When one goes up, the other goes down. Atomic radius increases when moving down the periodic table and decreases and moving to the right. Ionization energy, on the other hand, decreases when moving down the periodic table and increases when moving to the right. Compare the ionization energies for magnesium, aluminum, and silicon. First, you find Coulomb's equation for each, making sure you take into account the effective nuclear charge, which for magnesium, the effective nuclear charge would be 2, aluminum 3, silicon 4. Then order the elements in increasing ionization energy. So that would be from smaller force to greater force. So the increasing order of ionization energies is magnesium is less than aluminum, which is less than silicon, because silicon is holding on to its valence electrons a lot stronger because there's a stronger stronger force between the nucleus and the valence electrons. So here's our order. The least ionization energy is magnesium. The nucleus is holding on to them the least. Aluminum a little more, and silicon holds on to those valence electrons the most. We have demonstrated with 3 elements that Z effective will increase and the force on electrons increase as you go across a period. This makes it harder for an electron to be taken away, so the ionization energy increases as you go across a period. You can see for this cool 3-dimensional chart how the ionization energies get greater. Right? Here's the yellow guys, here they're small, gets bigger with blue, bigger with purple, bigger with the light blue, and it just keeps increasing. Also, and we didn't cover this yet, but you'll see that the ionization energy also increases as you go down the family. We're going to do that next. So here's a chart of first ionization energy versus atomic number. And very nicely, as you go across a period, you can see it increasing. And then when you drop down a group, you can see it go down, just like we showed. However, life and chemistry and physics are never that simple. And there are 2 apparent discontinuities in this trend. Can you see them? Let me first erase the arrow so you can get a better look. So take a look and see if you can find out where this is problematic. The first discontinuity is between groups 2 and 13. And you can see on the chart to the right, and let's highlight that for you. There's one discontinuity and there's the other one. And then we're just going to click on and tell you what elements we're dealing with there. We have beryllium and boron and magnesium and aluminum. The ionization energy actually decreases when you go from group 2. Group 2 is going to be beryllium and magnesium. And then group 13 is boron and aluminum. So please have your periodic chart out while we're looking at this. So again, the ionization energy decreases going from group 2 to group 13. The electron removed for group 13 elements for your first ionization energy is from a p orbital. And removing this electron actually adds stability. The atom gains stability by having a full s orbital and an empty p orbital, and we talked about that a few units ago. More energy is required to remove an electron from group 2 elements than group 13 elements, and you can see this by drawing the orbital diagrams for group 2 boron and group 13 beryllium to understand why. So go ahead and draw them, please, and in a second we'll pull out the answer tab to see what we have. Okay, we have boron with 5 electrons, and here's the electron in the p shell. That's relatively easy to move away because it's not in an occupied shell. It has no partner. Beryllium is okay. It's got a 1s2, 2s2. That's very stable. So boron will gain stability by having a full s orbital and an empty p orbital. The next discontinuity is between groups 15 and 16. And we can see that here in the red circles. So use your knowledge of electron configurations and atom stability to explain why that happens. Well, what we need, first we come up with our electron configurations. Okay, should have said that the first circle there is nitrogen and oxygen between groups 15 and 16. The second circle is phosphorus and sulfur. So if you look at the configurations, nitrogen, which is the group 15 here, and phosphorus both have half-full sublevels with the 2p3, and in this case, phosphorus, the 3p3. Oxygen and sulfur will gain more stability by giving up an electron so that they have a half-filled subshell. So let's see if the answer agrees with us. Yep, group 15 is more stable because it has a half-full sublevel. All elements but hydrogen have multiple electrons. As a result, we need to distinguish between the first, second, third, etc. ionization energies. Each successive ionization energy is always higher than the previous due to the higher nuclear charge experienced by the remaining electrons. So let's look at sodium here. The first ionization energy is 496 kilojoules per mole. Look at the jump, almost 10 times as much for removing that second electron to make sodium 2+. After sodium loses its first electron, it is isoelectronic with neon. Neon has extremely stable, full S&P subshells and minimal shielding. It requires more energy to remove each successive electron. So the second ionization energy greater than the first, the third greater than the second, etc. When all valence electrons have been removed, leaving the atom with a full p subshell, the ionization energy becomes incredibly large.